Um, Today we will continue with array antennas. So we will talk about how to synthesize patterns for array antennas. So what we did on Monday was really to come into the concept of what is an array antenna and what do we use an array antenna for, and then we introduced this array factor. We also looked at some of the properties of arrays, typically what was called a uniform array. We saw it had a main beam, it had some side lobes, and if you increase the spacing, you get grating lobes, which means basically there are many main lobes inside of it. And then we got some feeling for, in some ways, how do we phase shift the elements to get specific radiation patterns. And what we will do today is to really move on those radiation patterns. So it is the question here how to get the pattern we would like to have from the array. And that depends on, of course, that we would like to have a specific shape on the pattern, but also that we would like to direct it in different directions. And we should have a feeling for it ourselves. That I talked about this, that we could change the phase 180 degrees, and then we can steer the pattern. But we should, of course, also be able to calculate that for any direction we would like to do. And that we're going to cover today, with many other things in some ways. So the outline of this is really pattern synthesis, array steering, and then some methods here to actually get specific radiation patterns. We will talk a little bit of superdirectivity, and probably below here it should continue because we will also talk about MIMO. So in MIMO, that is really array antennas. So that will come also here afterwards, even if it's not in the outline. So if we look at our antennas, and we can see different goals of having antennas, what we would like to do with them. And one example is that you have a satellite antenna. So of course you have now an antenna that sits somewhere up in space, and you would like either to transmit, for example, internet is coming nowadays, but the typical one is TV. You want to broadcast TV inside of from a satellite. And of course, then you can say, I would like to now broadcast it, and I can just shoot it down on Earth. And then, of course, you can get a main lobe that looks like this. If you just think that you take your patch antenna, for example, how does it directed? And then you would cover this region. But if you look at this region, very few people live out here. So maybe you don't want to waste your radiation to where you don't have your users. So you would instead like to say, I want to illuminate all my customers that maybe sits here, for example. And then I want to shape the pattern so these people receive the signals in some ways. So I want to really have illumination of some specific regions. So I don't need to synthesize a pattern that do that. I can do it by having an array, and I can do it by having an antenna with a specific radiation property. In other cases, you would like to have, for example, a very narrow beam width and also low side lobe levels. So for example, point-to-point communication. So if you have a base station sitting here, you have another base station here. The two base stations actually communicate also with each other in many cases. And then you would like to have a very narrow beam, so you basically only send the signals between these. You don't waste it outside. Low side lobe levels, narrow beam width. There will always be some signal outside it, but as little as possible. Electronic scanning that we can see here, that's of course very good in many cases, and it's coming now in everything in 5G. People talk about 6G and up, and of course in all of these cases you can adapt your radiation to where your, for example, users are. Alternatively, if you have a radar antenna, you can have some airplane coming up here. Then you have one airplane there, one there, and so on, and you want to follow them in real time. So you want to have the beams going in different directions. If you have a MIMO antenna, you typically would like to have orthogonal radiation patterns, or at least radiation patterns that looks different in some ways. And that means that they can then collect radiation from different directions and get different type of information from it. That we will look at when we come to MIMO in the end of this. So you have diversity there. So there are many cases where we would like to shape patterns for specific applications. And in many cases, doing these things can be for an antenna, if we were sitting what we did previous weeks, that is that you would like to control the current on your antenna. And now you have been designing your own patch antenna, and of course your patch antenna radiates and so on, but you also notice that it's pretty tricky to actually get the current to be in any specific way. In some ways, it's not simple to say the current should be like this here and should be something else on another piece of the patch. The current is in some ways what it is. But if you have an array, you have a huge advantage, because in the array you have these excitation coefficients, which is the signal that comes in the signal to the array antenna. If you have, for example, a full MIMO system, you can typically control both the amplitude and phase of that signal. You can control anything on it. And then you can actually do a lot of things. So there we can say what excitation coefficients are good to give a specific radiation pattern, for example, or to communicate efficiently to its users, to beamform to all of them in some ways. In some applications, you can only control the phase of them, which means you control basically the time delay of these signals. And in that case, you can do anyway these what we have up here with this electronic beam steering. You only need the phase to do that. You don't need the amplitude to do that. You can have a fixed amplitude case. And that will be the majority of what we will do in the beginning of these lectures. So not controlling really everything there. We will say that for steering, we only control the phase. And then we use the amplitude to give a good radiation pattern. We divide it into two cases then. So if we think what is happening now to be able to steer your signal in a specific direction, we need to have a feeling for what we should do in these cases. And I think I have said it many, many times that the only thing that really matters in these cases is the distance from your antenna to your receiver. And since your antenna now is large in terms of wavelengths, it's like, you know, more than half a wavelength if it's typically array, it really matters the distance within the antenna. And that is what's happening. If we want to control this, we need to use that, that we can send signals a little bit earlier from some places, later from others, which is the same that we can control the phase of them. So if we think what we have in a typical case here, if we focus first on this left part of it here, so we say that we send the signals from all elements at the same time. And that is what I have drawn down here. So at a certain time, I just send a signal. You can say you send like a ping. So, and then that propagates out. It will be the same if it's an electromagnetic wave or an acoustic wave. It doesn't matter. It propagates with some finite speed. And I now send it just all elements at once. And if I do that in this case, all of them will then, of course, the wavefront will move forward a certain distance when time moves up. And in these cases, I just make it move in a direction straight out here. So if I have the same excitation of all elements, it will radiate in a direction which I call broadside here, which is straight out from the antenna. That is the broadside radiation. You send the signal at the same time from all elements. And the reason that it propagates in this direction is that if you take a point here that is far away and you measure the distance from all your antenna elements to this point, when the point is far away, it is the same distance, which means it takes the same time for the antenna signal to leave the antenna and go to the receiver. Then they add up at the same time. If we instead focus on the other curve, so the one to the right, so look at this one, then I do something else. So now I send the signals at different instances in time. So time is moving up here. So at some time, the first time, which is now a negative time in the scale I have here, I send this blue signal. I send this one. So first I send that one. And that means that that starts propagating here, and the signal then moves along because it goes with the speed of light if it's an electromagnetic wave. A little bit time later, I start the next signal that sits there. That's this one here. And then that type propagates slightly shorter. And at the latest time, I start with the red one that sits up here. So there's a time difference in these ones. This is some like delta t from where I send the first instance to the last one. And the red one is there. It has not even started yet in the drawing I have here. So I send the signal at different instances of time. And then when I move forward, of course, all of these signals propagate with the same speed. So they move the same distance. But since this one here started late and this one down here started early, I get the direction of this that is not in the broadside direction. I get the steered version of this one. And that is how I steer the direction of my array. I just use the instant in time when I send the signal. And of course, an instant in time means it's an instant of phase. So I change the phase of these elements because we typically talk here about time harmonic signal. I send a signal at 1 gigahertz or 100 gigahertz. So I just change the phase of them. And then changing that phase, I can change the direction. Because if you sit here now as a receiver, it's always closer to this element than this one. It is that local difference in distance. And if it's further away to signal, to reach at the same time to my receiver up here, I need to send this signal slightly earlier. That is the basic principle between all of this, which is what you should really understand. Then we will learn a formula who tells you how to do this. And the formula is of course important, but the basic understanding is even more important. This is how you control the direction of your radiation in some ways. So if I just move on here in time, you see, it propagates in different directions. So now if I then just want to write this up, because now we want to have a formula that is doing these things, I can write up my array factor. And we derived the array factor on the previous lecture. And now I have this Z-directed 1D array, which means I have just elements here in the vertical directions. And each of these elements here, some antennas, they receive a specific signal, and they receive this signal AN. So the first one is then A0, and then A1 and A2 when I move up. So they get different signals. And then what sits up here in the rest of this formula, this e raised to n kd cosine theta, is then the distance to the receiver as a function of the theta angle. So my receiver can sit up here, and then I have a theta angle that sits between them. So that is what will measure that local distance between all of those elements. How much further is it from one element to another one? It's not the total distance, it is the relative distance between all of these elements. And if I now take this is a big sum of coefficients and of course different directions. I can just write this, that I take this one and I multiply with all of the coefficients. So instead of writing a sum, I can write this as a product between two matrices or two vectors, depending how we would like to see that. And I call those f of theta times the excitation coefficients A. So I collect all of these elements here. These ones I call into this boldface A. So that is a vector or a matrix, depending how you would like to see that, of these coefficients. So that is just rewriting my array factor in these cases. And now you can ask the question, now I have a way to do this. So I can say, of course, this radiation pattern or array factor in different directions depends only on my coefficients. So the question is really, what would I like to do with my coefficients? Because my coefficients I can control. And if I can control them, I can get different things. So of course, now I should just say, what would I like to do them? And then I should try to solve that problem. So it's doing what I would like to do. That is the purpose. So what would you like to do with an array factor? Because now we have an array here. What would you like to do in a typical case here? We will do this as a poll, so we will discuss this. So you have a question here now, A to E. So what would you like to do? Do you like to typically, I mean, difference in different applications, but maybe direct the radiation in some directions? Maybe you would like to not direct it in other directions. Maybe you would like to have a very large amplitude of these coefficients as it's there. Maybe you would like to have the coefficients down here equal to 0 for some of them. Or maybe you would just have that these ones are very small in some ways. So they're smaller than some number. Because now what we have learned is, of course, we can write up array factors and we're going to do something with them. But what would you like to do? And maybe if we know what we can do, we can just determine these array factors so they are doing what we would like it to do. That is the purpose of this. So you have this A, B, and C, and D. Figure out what you think you would like to do with an array pattern. And we will start this as a poll. So I will launch the poll, and you know now what A, B, C, D is because they will disappear. And fill out what you think that you would like them to do. So what is in some ways the purpose of an antenna or communication system? What would you like to do with it? So the A case, radiation in one or several directions. B, no radiation in some directions. C, large amplitudes of the excitation coefficient. D, zero amplitude of some excitation coefficients. And E, low amplitude in general of the excitation coefficients. What would you like to have on them? So we have 56% of the votes, so a few more. I keep it open 10 more seconds. Okay, we will close it down now. So here you can see the result. A dominant one that you direct the radiation in some direction. Some also thinks we would like to have no radiation in some directions. And also equally many have large amplitudes of the excitation coefficients. Zero amplitude also for some, and in general low amplitude was very few. And in this case, what you typically would like to have is definitely what you have A. You want to direct your radiation. That you would like to do. But in many cases, you actually would like to also have no radiation in some directions. That's very common, or at least low radiation in some directions. So B is very common. Large amplitude of excitation coefficients. Why would you like to have a large amplitude of the excitation coefficients? Of course, you could say I want a large amplitude because it has I transmit a lot of power on them, but why would you like to do that only on some of the antennas? Would you really like to do that? No. You would actually have the coefficient basically as low as possible. So C, typically you don't want to do. D, zero amplitude of the excitation coefficients. No, you don't want to do that because, I mean, you built an array. You have a lot of elements that can transmit. Why should I say I don't use two of them, for example? If you put zero amplitude on them, you don't use them. Then you didn't have to build those in your array. So typically you don't want to do that. But now I should stop this one here so you can see them. But the last case, E here, to have low amplitude of the excitation coefficients, you typically would like to do. So absolutely in these ones, you have A, you have B, and you have D. That is typically what you like to do. And there are many variations of this. I mean, you want to send direction in some user. I have in this direction, I want to send the radiation there. If I have a jammer or I have another user at a different place, I would maybe like to reduce the interference with that one. Then you don't send any radiation in that direction, or at least very low radiation in that direction. Large amplitudes, no, you don't want to have it. Zero amplitude, you typically don't want to have it. You would like to have as low amplitude as possible on the excitation coefficient, because that is the power that your amplifier drive to your antennas. And you typically want to have it as low as possible, but still send as much radiation as you can. Keep it equal between them and low amplitudes. So typically the same power to all elements is the best that you can do in this case. So these are the typical ones that you would like to have in these cases. So now comes the question, of course, how do we do this? How can I control that I have maximum radiation in some direction, that my amplitudes are small? And I will show you different ways of doing this. Some that is we can do by paper and pen, some that we need a computer to do in some ways. But we should understand the different concepts to control this radiation. And in general, you should understand that this is the way that you control your radiation. That is by controlling these excitation coefficients. And then you try to do something you can with this array factor. And we have a relationship between them that is known. So this is what we can use. Okay, so if we see this, yeah, we typically, again, the same thing. We would like to radiate in one or several directions. That means that I would like to make this one large, because that is my array factor. That is the one that sits there. So if you make that large, you radiate direction in that direction. If you, in these cases, now keep these ones small, they could be 0, or you could have low radiation in other ones. Yeah, you need to make this one small instead. So for some thetas, large, other thetas, small. And of course, the different thetas is different combinations of this vector or matrix that sits in front of it. And if you would like to have relatively small excitation coefficients, you should say that all of these are below some certain threshold. And we will see in the end that this is an optimization problem that we can actually feed to a computer and let the computer decide what you should do with it. So we can actually change the direction of this and saying, like, we as the designer of the system can say we would like to have this, and we let the computer then decide how to do it. And that's really a direction where much of this is moving. But there are really good simple formulas that actually does this for us. So we will look at those ones, because those are the ones that are in use. They will be used a lot forever in some ways. But in many cases, we can let the computer do it slightly better. So if we now start with the first case, let's say we would like to steer the direction in some directions. So again, we have what we had before. We can write the array factor here as sum f, which is just these numbers that we had before. And I have my excitation coefficient. So now I can ask the direction, how should I adjust the direction of how should I adjust the phase of my elements so I steer the radiation in a different direction? And I would like to steer them now towards a direction θ0. How should I do that? So one example is, for example, here that we have broadside and it's in 90 degrees, end fire here, it radiates in straight up, that is at 0 degrees. How do I do this steering at different angles? And we can see here that it's coming in is really these phase factors that depends on this angle. So we should now determine then these coefficients. So that in some ways they have an amplitude 1 in one direction I would like to have. And I would like to have my coefficients small. And now I measure the small that I have n elements. I would like to make the amplitude of each coefficient 1 over n. So if I had 2 elements, I put half signal in one and half signal in the other one in amplitude. But I can control the phase between them. So we start with a uniform array. And a solution of doing this is actually to put it in as the Hermitian transpose of the elements. So if I have here my A that sits here, I can write that as my coefficients. I weight that with some matrix f theta that I know what it is. And if I multiply this f theta by itself, I get 1 over n, or I get n. And then I divide by n, and that is the number I have, I get 1. And that's actually the solution to my problem. So this is a mathematical way of actually doing exactly what I showed you in this illustration before, where I said I would change the phase of these elements with only this local distance that comes in. This distance to my receiver and my antenna elements. That is the one that comes in here. And what I should do is basically phase conjugate it. So if you remember that picture, I receive a signal, and then I should in some ways, or I should transmit the signals at different times. I will show you in the next slide that that is the opposite from receiving and transmitting in some ways. It's called phase conjugation in these cases. So you phase conjugate your excitation coefficients, and you do it from the receiving point of view in these cases. So if we look what's happening then for an uniform array, so if I have a uniform array, I can compute all of these coefficients that I can put in to these ones. That is the phase. So the original phase is 1 on them. And now I should change them with the phase according to this cosine theta. So if I put in different values of these ones, so I can start with the broadside one here. So I say it should radiate straight out here. If I say I would like to have that radiation, that is not what is in the patent in these cases. What that says is that I should put in my theta 0 as 90 degrees. Cosine of 90 degrees is 0. So the phase factor here gives 0. And that means it's the same direction to all of, or distance to all of them. And all my coefficients is just 1 over n. And that is the patent that we will have very soon. That's the one we have there. That is the 90 degree. That is the patent that we saw on the lecture on Monday in some ways. So equal amplitude on all of them, but also equal phase. It radiates in the broadside direction. If we do the end fire direction of this one, so let's say it should go in the theta equal to 0, then I have to compute pi cosine theta 0, that is pi. I have to put in the distance that I have here, which is lambda over 2, and it says that the phase difference between each element is 180 degrees. I can plug that in, and it says here that my coefficient should then be -1, +1, -1, +1. So they change from plus sign to minus sign in that case. And that is due to that in this element that I have, if I have it in the z direction, the distance here is lambda over 2, and lambda over 2 is 180 degrees. So if I look at radiation in this direction, I need to add another 180 degrees to get constructive interference in that direction. That we also saw on Monday. That is how we need to change these elements. And that was in this case the first one as it's done. So that is at 0 degree. And then of course plugging in another theta, I can do 30 degrees. Now you can see my radiation is start moving in this direction. I can do 60 degrees, it just starts moving these elements. 90 degrees, I can move up here 120 degrees, 150 degrees, or 150 and 180 degrees. And the only thing I change on the element is the phase. They have the same amplitude all the time. So I just give a different phase to all of those signals and I get the radiation to move. And that is how you can steer the beam of your array. And if you now interpret this with the same way as we did before when we saw how we transmit these ones, we can see this is phase conjugation or time reversal. It's the same thing. In fixed frequency, it means you change the phase. And if you look at it in time, you change the direction of time. So if we focus on this left one here, now we can say that it comes in a wave here. This is the wavefront, so it's coming from this direction. And then I receive all of those signals at the same time. So at the moment, I have not received the signal yet because it has not reached my antenna. It's propagating in this direction. If I move up one time step, it's basically at the antenna. So that is what we can see here. I receive the signal, and then at the next one, it's past me. So I don't receive any more signal. So this is now as a function of time. And then, of course, it just continues to move here. If I do the same thing for this one that is now in a slightly different direction, so we focus on this one, then the wave is coming from this direction. And then, of course, I will first receive a signal at element 1, the red element. And that is what I can see here. I receive that signal slightly after time 1. And then it will take some time before I can receive, for example, this element down here, an element there, because of course the wave has to propagate a longer distance. So it takes a little bit time to reach that element. So if I move here, now I receive the first signal. So I have it now in the red element. Now I start getting it in the purple element. And now I have received it at time equal to 3. I also received it in the blue element over there. So the closest element receives it first, the one further away receives it later. And now, of course, if I'm going to send the signal back in the same direction, what I do is that I take this blue one and I put it first, and I take the red one and put it slightly afterwards in some ways. So I change the order of these ones. So I send the red one, or the blue one, before I send the red one. That is, I do time reversal. I change the order of time in these cases. So this is how I transmit it. Now you can see I flipped the direction of all of these elements. So I receive them out here. I first receive the red element, and then I send it the last one. So the order in the left one is red to blue. That's how I receive it. How I transmit it is I send first a signal from the blue and then later from the red. And then I get the direction here to go back from where it came. It came in from that direction. I transmit in the same direction back. This is time reversal or time phase conjugation, how you send it. And if I do that, I make it propagate in the direction back towards the receiver. It's a very general principle. You can really use it in many cases. You can have a random scattering of events. You don't know how it hits different walls. The signal have then propagated different lengths. And if you wanted to go back in that path and do the same, tracing and hitting those walls and then ending up at one point, you need to send it slightly before the signal that maybe go line of sight. This is a time reversal of this phase conjugation. Very general principle in these cases. So that is some of the ideas who sits there. And now what we're going to do is to synthesize arrays that do these cases. So we will look at some cases now that we know now how to steer them. But now I would like to have different radiation patterns. This is the uniform array. That's the one we've been looking at. The red bars here, they show in these cases the coefficients. So the amplitude of the coefficients are all the same in this case. Then here comes a new array. This is what's called a binomial array. We will look at that one. And now you can see that the side lobe disappeared. And what I paid for price in these cases is that I have different amplitudes of my excitation coefficients. We will look at the last one, which is the Dolf-Chebyshev in these cases. And now you can see I have lower side lobes and I have a different tapering of the excitation coefficients. And by changing the amplitude of the coefficients, not the phase gives the direction, the amplitude can control the side lobe level in these cases. We will also look at one method here, which is called the Shelkonov zero placement method, which is a simple method to say that I don't radiate in a certain number of directions. So we will look at these methods. And then there are other methods here. You can see Fourier series, Woodward-Lawson. There are many of these ones that we can do. We will do a general one in the end, where we actually say where we almost back where we say what we would like to do. And I will show you that we can formulate that as optimization problems that the computer can solve for us. We will also look at that. Okay, so if we now have this prescribed array factor, so I say that I have n elements from my linear array, so n antenna elements, and I would like now to radiate here in m different directions. So that means that I say that I know what am should be. It's just a matrix vector I can write up here for all of these different directions. And if I do that, it means that this is basically a linear system, because all of those multiply my coefficients and they are equal in the right to what I would like to have. And of course, now if this is a square matrix, so equal number of n here elements and m directions, I could just invert the matrix and it will tell me my coefficients are. That is usually not the most practical way of doing it. But it is really like a matrix system. So it's a linear system with m equations and n unknowns. And you know that you have unique solutions if those are equal. We will first do the Shelkonov zero placement method. And that means that, of course, you don't want to have the solution don't radiate anything. So there you say that you specify only one less constraint. So in these cases, you have the number of directions is one less than the number of elements. And that you will do in the Shelkonov zero placement method. So let's start with that one. And that is the first synthesis method we have for these arrays. And this is a method that is based on specifying m directions here. And then you have one more element. So the number of elements you have is one more than the directions. And then we just use one property. So if you remember what we've seen from all of those array factors, they are e raised to a coefficient a times e raised to something. And we can write that with these digital wave numbers here. So if I just call it z, then it's zn is e raised to j phi n. And this will now be a polynomial. So my array factor here, I can interpret as a polynomial in these coefficients. What do you know about polynomials? I think in high school you learned you can solve a second order polynomial. It has 2 zeros. A third order polynomials have 3 zeros. What does the Shelkonov zero placement method? It says specify the zero and then determine the polynomial. The polynomial are the excitation coefficient, give the zeros, and then you have the Shelkonov zero placement method. So you rewrite these polynomials as a product in all the zeros. That is Shelkonov zero placement method in these cases. And the zeros are now given here by these digital wave numbers that says I would like to have a 0 in that direction. So the psi n is this kd cosine theta n. So we will show how we can do that in an example. If we look at just one case here first, the first one is here now, theta n is 30 degrees. So you can see here now I have specified a 0 in this direction, and I get the radiation pattern that has a 0 in that direction. Now I can add one more. So let's say now I also have a 0 at 60 degrees. I change my radiation pattern a little bit. I don't know where my main beam is. I know where the zeros are. Add a 0 at 100 degrees. You can see you get a new radiation pattern. Add one at 120 degrees, and then one in the end at 180 degrees. So every time I just add one of these zeros, I get a new radiation pattern. The bad thing with this is, of course, I don't know where it radiates. I only know where the zeros are. So in a practical case, things about jammers or something that you should not radiate in that direction. And how do we do it in practice if we would like to do this? So let's look at one example here. So again, we have this linear array, one-dimensional array, and we should construct a radiation pattern that has zeros at 60 degrees and at 180 degrees. And we have lambda over 2 element spacing. So we have 2 zeros. The first question here is, how many elements do we need? And what we just saw is that we need one more element than we have zeros. That is what we need to specify. Then we're going to determine the excitation coefficients and plot the array factor. So let's do this case here. So we can see that we have 2 zeros. There are 2 roots. So it's a polynomial of second degree. And that means that if it is second degree, you have 3 coefficients. And each coefficient is the excitation coefficient for your array. So you need 3 antenna elements for this case. And how to compute them, there we need some math to do this. You will do it in exercises. You have to just follow the procedure of writing up these psi, the digital wave numbers. You form your theta, and then you make a polynomial out of it. So in our case, we have two zeros. If we first have this theta 1 at pi over 3, then I can compute my z1. And then I have to compute, of course, what is cosine pi over 3. I have to multiply that with pi and then do e raised to that one. And doing that, I get that z1 is equal to j. So you can see you go from the direction, and then you compute what is the 0 theta in this case. The next one was at equal to pi, so theta 2 is pi. Then you do cosine pi, that is -1. And then you get e raised to j pi, which is equal to -1. So I have two zeros now, j and -1. And then I just form the array factor here. So that is z minus z1 times z minus z2. I multiply it together. I get all of these that sits there. And then I just identify my coefficients. Because if I have this one now, I can see that the lowest order term there, this is the term that is z to the power of 0. That is the coefficient that gives these ones, which is then a0 in this case. So then I can read off that is minus j, and then my coefficient is minus j. Similar way, I do it with the next one that sits here. I get a1 and I get a2. And then I have my array factor. Isn't it brilliant? So what you do is like give the directions, compute cosine or something, do e raised to these ones. You get some complex numbers, you multiply them together, and actually you have your array factor. Extremely abstract, but at the same time extremely beautiful. And what you of course need to do this when you do it is this picture here of the complex plane. You have a real part, you have imaginary part, and if you have some angle here, this is I, this is minus I, this is -1, this is 1, and then you have some angle that sits between those. So you have to identify where you are from this Euler's formula, usually e raised to minus j pi, then the angle is pi, and you sit out here, and that is -1. So we have to identify those ones, and we actually get out here what is the array factor. So that is our first method. We will also look now at more methods. So you saw one method I showed you in the picture is that we could remove the side lobes. And you can remove the side lobes with what's called a binomial array. And the binomial array is a specific choice of these excitation coefficients. So now we start saying, which excitation coefficient should I do? And this is actually identical to the Shelkonov zero placement method. Because if you look here at one of them, look at this pattern that we have here. There are no side lobes. So really only one main lobe. The main lobe is rather wide and no side lobes. So where are all the zeros? Yeah, the zero direction is here. And of course, by symmetry also straighten. So there is a lot of zeros at 0 degree. And that means that this is a Shelkonov synthesis with multiple zeros. And that means that my array factor in this case can be written as just z plus 1 to the power of n. And this is this binomial array where you can get all the coefficients from something called Pascal's triangle. So here we can use what we know, that if we have, for example, z plus 1 to the power of 2, then we go down here, and then the first coefficient is 1, the second coefficient is 2, the third coefficient is 1. And then I would have 3 elements, and that is the one that is plotted here. So this is the radiation pattern from a binomial array with 3 elements. And in red here, what you can see is the individual weights on that one. So the edge element is 1, the next element is 2, and those are the one that you have up there. And now you could see again, yeah, very wide main beam, no side lobes. Perfect, beautiful, because we don't like side lobes. Of course, we don't like a wide main beam either. Both are bad in some ways. When I take this and I increase the number of elements, so we go to 4 elements. So now we are sitting up here. This is 4th element here. Then you have coefficient 1, 3, 3, 1, and you can see the relative scale down there. So in some ways, what we do now is that we taper these coefficients. We try to make them smooth. They don't go from 0, strong amplitude. They go from like 0, smaller amplitude, larger amplitude in the middle, and then smaller again. And the effect was that the side lobe disappeared. We can move on here. I can just move on. You can see the general shape of all of these cases. So this is the binomial array. No side lobes, very easy to synthesize, but of course it has some problems. And one problem here is really, if you look at these coefficients here, at the end elements here, you basically send nothing. This is the signal. So the middle element here would have an amplitude of 20. The edge element has an amplitude of 1. If you think about powers, then you should square this. So the power would be corresponding to 400 in the center element and 1 on the edge element. And of course, that's a waste. So you would like to go somewhere between. And in practical cases, yes, it's nice to remove these side lobes, but maybe we don't have to remove them totally. Maybe we can pay a price and just making them small instead. And that will be called a Dolch-Chebyshev synthesis or pattern that we will see very soon in this case. Okay, so with that, before we go into this Dolch-Chebyshev, we will take a break, and then we'll continue with this one after the break. And the Dolch-Chebyshev here is the middle way between the binomial array and the uniform array. You get the best of both worlds in some ways. But let's do that after the break. So